So what is DTrace? DTrace is instrumentation engine, dynamic instrumentation engine for Solaris. It was made by the Brian Cantrell, Mike Shapiro, and Adam Leventhal in 2005. And then it was introduced to some BSD systems, like FreeBSD and NetBSD. And along with it, it was then added to OS X, which is loosely based on the FreeBSD. Particularly for OS X, it was included in 2007 in 2.5 version of OS X, codename Leopard. And any developer might know DTrace from the instruments tool for OS X. Stability was the core assumption for DTrace because this engine was was to be included into the Solaris, and Solaris is for servers. So you can't actually break the system because, well, that would be not very good. And the second one was the no overhead. So the applications that are not traced need to work exactly like they would work if DTrace was not present at the system at all. And they actually achieved that. However, in order to do so, they needed to remove some parts, some interesting parts from the D language. And that's why I say that it's kind of retarded debugger / DBI engine, because you can't do everything with DTrace. For some things, you actually need to use any sort of a debugger or actual DBI engine. For example, Pintool or Dynamically. So this is a DTrace mascot. Nice, nice. And that's how the basic D script looks like. So you have a provider which generally provides you with some vague functionality. Then you have, for example, PID. Then you have a module. So for PID, you could actually trace some particular code chunks inside of dynamic library, and that would go for module. Then function, well, this is self-explanatory, and name, which stands for the semantic meaning. So for example, if you have some kind of a function, then name could be, for example, entry and return. So for every entry of this function, make some actions that are defined. And one more thing about functions. As you may probably know, you could deduce that you actually need to have, you can't have striped binaries. So you need to have symbols in your binaries. I mean, kind of. Then you have a predicate, which is the only form of if statements in the D, and you have actions. So all that you can also run as a one-liner from the command line. So the other one is just a one-liner, but basically does the same. So yeah, that's how it looks like. So for example, here you have a DTrace provider, and two fields are just left out, module and function, and you have a begin. So begin would fire for the entry point of the DTrace script itself. So for example, if you want to make some kind of a formatting, then you can do that by a DTrace begin, and also DTrace end if you want to do something at the end of the DTrace script. So the architecture looks like this. You have scripts or one-liners that go to DTrace command, which is basically the DTrace consumer. You could technically code your own consumer, for example, in Python, and that would be Python bindings. And that makes the DIF, which is, no, that actually parses in the script. The DIF is made by libdtrace, which is still in user space, but it sends the objects into the kernel land for DTrace driver to actually schedule stuff for the DTrace providers. Yeah. And as a bonus, you have something like USDTs, which are user-level statically defined tracing. Basically, you can make some static points in your own programs or in programs of other people, and put probes statically into the code. And this actually is quite interesting because, for example, if you have a JavaScript provider, which is JS, then people from Mozilla introduce DTrace USDTs into Mozilla Firefox, and you could peek into the internals of the JavaScript via DTrace, and it would be enhanced even more if you would do that via USDT than if you wouldn't have USDT at all and you would just try to go dynamically via bare DTrace. And that's because you wouldn't have the underlying meaning. OK, so that's a D language. Basically, D is like C, so if you know C, then D will be easy to learn. Data types, so basically like C, anyone knows that. One important part is that you can dereference pointers, and that means that you can walk structure chains, and you can cast things. But you can cast things in C and dereference also, so. Yep, and types of scalars, types are scalars, strings, arrays, and associative arrays. Scalars are usual just values. Strings, that is kind of different than C because, well, it's more like Python strings or whatever higher level language. Then you have arrays, which are like C, and then you have associative arrays that are not like C because you use tuples inside of them. And you have a kind of different scope than in C, and you use variables in a different way, as you can see. So if you want to have a global variable, then you just use name, but without any type. If you want to have closed locals, then you use this arrow foo. If you want to have thread locals, then you use self arrow bar. And if you want to reference to external variables, you can do that by backtick. And yeah, as an example, you can actually go for the kernel variables. Interesting built-ins. So the DTrace, of course, they needed to introduce some kind of a functionality that you can use, some kind of additional data. And that comes in the form of built-ins. So you have like 3 pointers to typical structures for processes and threads in Unix systems. So you can reference some interesting values inside of those structures. So those are carps info, which is for processes, carl vps info, which is kind of for lightweight processes, and car thread, which is current thread, which is for threads. Then you have a color. Well, color is just a function that calls the function that you're actually probing. You can reference arguments, exec names, PIDs. PPIDs are parent process IDs. You can use timestamps, and interesting part is that you can actually dump the registers, but you cannot modify them. And actually, OK, I have this example later in the slide, so OK. Operators, well, these are exactly like C, apart from strings and XORs. As you can see, for logical XOR, you have double dashes. Yeah, birds. And for bitwise, you have just one. So for bitwise, it is normal. You don't have loops and you don't have ifs because, as I stated earlier, you actually cannot have them from the assumptions. Because if you would have loops or ifs, then you could do never-ending loops or ifs. So that would be very bad for a production system. However, there are reserved keywords inside of DTrace. So you have keywords for do while, fors, gotos, ifs, elses, but they didn't actually implement that, or at least they didn't do that for public. Actions and subroutines, these are also kind of built-ins into the DTrace. So you can dump the stack. uStack is for user mode, because in DTrace, when you're tracing any application, you do that from inside of the kernel, and if it's in the user mode, then you would have different stacks for the actual DTrace probe, which is in kernel land, and different stack for the application that you want to have stack for. So then you would use user stack. TraceMem is for tracing general pointers, so you can trace memory. Allocations, bcopies are, well, for internal usage of things. Then you have copy in, copy inst, and copy into. As I said just a second ago, the DTrace is in the kernel, so if you want to have something from user mode, for example, you want to have a string that is pointed by the argument, then you need to somehow copy it into the kernel. And you would do that via copy in. I have that in the example, so I will point that out later. And message sizes and string lengths, well, that kind of relates to allocs and bcopies. Then you have destructive for specific processes. These are only available if you switch the pragma destructive, which are stop, raise, copy out, and system. Stop and raise are kind of self-explanatory. You can stop processes and raise some signal, for example, 9, which is kill. And copy out string is actually destructive because you can mangle the memory. So this actually was used by Nemo in his examples. I will provide the reference later. Where he, on x86, when you call functions, you usually do that via std call or cdecl. You don't usually do that via fast call. So you can actually change the things that are on the stack via copy out instruction. So you could, for example, tamper with the output of some applications. For x64, you could do that. Probably I didn't test that. You could do that if the argument is the pointer. So because on x64, the first 6 arguments are passed via registers. So you can't modify the register, but if the argument is a pointer, then you can dereference that pointer and then mangle with the memory pointed by the pointer. And system execs the, well, it's just like in C. It execs the application, provided string for the application. And for the whole systems are also destructive: breakpoint, panic, and chill. Breakpoint sets the breakpoint, and then it waits for the kernel debugger. So you shouldn't do that if you don't have a kernel debugger turned on. And panic, well, it panics the kernel. And chill is also interesting for race conditions, because you can, when you're analyzing race condition, then you can put some chills inside of the kernel, and well, you will win races more often than not. So it's good for analyzing vulnerabilities. And now we're going into providers. I don't know if you've noticed, I usually point only the interesting ones. So if you see the ellipses, then there are more, and you should check them. But for more interesting ones are like syscall, PID, Object-C, FBT, and proc. Syscall, you can trace any syscall on the system. For PID, you can trace, well, any process. For Object-C, this is kind of Apple-specific. You can go into the man DTrace, and you can read about Object-C provider. FBT stands for function boundary tracing, and is used to actually any function inside of the kernel. So you can peek into the kernel via FBT, and it's quite interesting. And proc, well, I actually used proc only once, and I've seen it in a very interesting usage, which was done a couple of weeks ago for LaunchD vulnerability analysis, because the guy had a kernel vulnerability, but the Apple, as usual, didn't release the kernel with debug symbols. Yep. And he couldn't actually connect, and he wanted to know where the crash is happening. So he used the proc, because with proc you can say that, yeah, okay, at the point of the crash for some process, dump the, for example, stack and registers. And he did that. It made things simpler. This is the output. Well, I will run through this. So basically, you are listing all the providers on the system via dtrace -L. Then awk is used to focus only on the second column. Then I'm grepping for the provider that I want to show, for example, PID, and then I count it. So for PID, you have 0, because I didn't trace anything. But for syscalls, you have 980. And well, FBT kind of stands out with 100,000. So yeah, it's pretty rich. Past work. Black Hat 2008. Tiller and David introduced framework Retrace, where they showed some appliances of DTrace into the vulnerability research, but it was kind of pretty simple. They just caught some stack-based buffer overflows and some basic heap stuff. And then Nemo at Infiltrate 2013, he, on the other hand, presented rootkit-like capabilities possible with DTrace. Not very useful. I wouldn't do anything like that with DTrace, because it misses the point. You can actually just, turn the DTrace off. But he presented a lot of interesting one-liners and ideas, and they're worth checking out. And similar projects, if you happen to be on Linux, then you can use SystemTop, which is very similar. And actually, it's kind of semi-compatible with the semantics of DTrace, because Red Hat wanted to do that in this way. For interesting usage case, you can reference to our blog post. And detours, this was kind of started before DTrace, or in the same years, in the past decade, well, 90s. And this is actually funny, because if you've reversed any DLLs from Microsoft, you probably seen the mov EDI instruction in the function prologue. This is actually hot patch for the detours. So it does introduce overhead, but it's very slight. You can read about MOV EDI at the provided link. So, usage. I will first run through some one-liners, then I will run through some scripts. So, this one just shows you the number of syscalls that were executed on the behalf of the PID. The PID in this example is a preview application on OS X that ran some test PNG. So you could see how many syscalls were executed. This is kind of interesting if you want to see, if you seek for any particular syscall. Not very interesting in general case. Or maybe if you're profiling the code, then it is interesting. The second one-liner tells us, okay, I will go back to this one. As you can see, I've left out the module and actual function, so I just put probe on any syscall that is in the system. And here I only put entry on the read syscall. That's why I only catch read, and I read the third argument, which is arg2, because we count from 0 in C, and I summon that. So the third argument is actually how many bytes the process was reading in that particular read function. This also is kind of not very informative in a general sense. Maybe if you want to analyze what exactly does the application is doing, then maybe it would be kind of interesting. Or if you have again, profiling the application, then you can pinpoint the bottlenecks. So why does it reading like 1 million bytes at this function? It shouldn't do that. And also, and I actually use that in my work a couple of times, you can trace any execution on the system. In this example, I trace the POSIX spawn, which is used on OS X, contrary to the usual execv. If you will trace only execv, then you will have kind of Apple-specific code chunks for, well, whole applications that does icon stuff, and you wouldn't catch that. So you actually need to put the probes on POSIX spawn, along with the timestamps. So it's interesting because Apple doesn't always does things straight. So it is interesting what exactly is happening in your system. You might be surprised. And for some more one-liners, you can either reference the provided link or just Google for them. There is really shitloads of resources on that, so no problem with finding this. And for scripts, well, scripts are kind of more logical or strategical approach. So if you want to develop a script, then you need to have an actual idea what do you want to do. So I will present the tracking input, memory allocation snooping, and heat tracing. Those are like general ideas that I wanted to study, and DTrace was helpful with that. So for tracking input, I've covered this on my blog a couple of weeks ago for read, but usually when the application is processing the input, you wouldn't just read the big file each time that you want to do something with it. You would usually memory map it and then reference that memory. It's faster. So I did that for mmap, and interesting problem arose in the OS X and DTrace particularly. And of course, you can track any input, so the same idea can be done for the network input to implement basic sniffer capabilities. So I will run through each DTrace chunk. So at the end, if you would glue every chunk, then you would have a working script. So in the begin, I introduced two global arrays in which I will be tracking the file descriptors and mmap pointers. Then for open, I'm starting to put two probes on entry and return, because on entry, I want to have the arguments that were provided to open, and on return, I want to have a return value, which is a file descriptor. I'm defining two thread local variables in the entry. So I'm saving the file name, which isn't required, and the other one is actually required because you want to have some kind of a flag that you actually went into the open, which you will use as a predicate in the return probe. So I'm using this as a predicate. Then I'm saving the returned file descriptor. I'm putting this into an array, but as you can see, I'm putting this in as an index. So I'm just saying, yeah, I have some kind of file descriptor, for example, 100, and I'm setting it to 1, so it is used. So I can later check that this file descriptor is actually used. And I'm freeing the used variables self fname and open OK, because if you make the variable 0, then you kind of deletes it. So that's that for open. For mmap, where I actually use the tracked fd as a predicate, again, because yeah, you probably don't know arguments for mmap, but the fifth argument is the file descriptor. So I'm checking if the tracked fd array of this file descriptor is flagged as open. And if it is, then I'm making some thread local variables that I will use in the return. Then I'm checking if any of the thread local variables are set, and because that would also could be just mfd, not msz. And I'm actually do some logging and use stacking in the upon the return. However, in my read example, I actually pick into the memory inside of the read return. However, on mmap return, I cannot do that. And that was strange to me. Apparently, with DTrace, you cannot pick into the memory that wasn't touched by the process. So even though mmap, well, the memory was actually touched because it was mapped, the process itself didn't touch it yet, so the DTrace can't dump it, even though the pointer is valid. So I'm checking the memory when I'm unmapping the mapped memory. So you check the memory via tracemem, then I copy in the pointer that I want to check, the reference. So I'm doing the copy in because you need to have the chunk from the user mode into the kernel mode, and then from this chunk you actually trace the memory, which is kind of not very elegant way, but it's how it works. So yeah, and then I'm just freeing the variables. And on open the close, I'm freeing the tracked fd, but you don't need to actually do that. For memory allocation snooping, I wanted to have a simple tool that imitates output of LTrace for memory allocations. And end goal was to use it for Realloc, which actually succeeded. However, the idea can be also re-implemented to make heap layout analysis or snooping into custom memory allocators or tracking kernel memory allocations. So for heap layout analysis, usually when you're exploiting some vulnerability these days, you have an ASLR, you have a bunch of other things that try to stop you. So you might not get 100% reliability, and then you want to know, well, okay, so how much reliability I do have. And yeah, you can do that with the debugger, but everyone knows that LLDB sucks. So you can also use DTrace for that. So yeah, basic workflow would look like this. You would, in case of the heap overflow, you would just play with the heap in the internal applications. So for example, in browser, you would use JavaScript, and then you would see how many times you have an object that you want to have at the address that you want to have it. Well, for browsers, it's kind of different game, but you could do that for any other applications that are not as easy to manipulate the heap as it is in the browsers. And then you actually need to use some kind of a functionality to research the reliability, well, the odds that you have with your objects. So this looks like that. I'm just putting some probes on each allocation functions. So for libc, these are malloc, valloc, calloc, realloc, and realloc F. Which so I put all of them into the slides, but they are just for the sake of the completeness. So I'm using the entry and return because on entry I have the requested size, and on return I have actually the memory pointer. So I need to have 2 probes for each function. And this actually is interesting. Well, why do they have Realloc F when they do have Realloc? Because apparently Realloc F is FreeBSD functionality and thus OS X, which frees the source buffer when it fails. So if you want to realloc some buffer and the reallocation fails, then realloc will not free the source buffer. It will just say, no, you will not have new chunks of memory. But Realloc F will also free the source buffer, which is interesting. And for free, you just, also for the sake of completeness, I just did that with void, because LTrace actually used the void, but the free function doesn't return anything. So yeah, it's basically void in C. But it's void, it's not string. So if you run it for bin ls, you have something like this in my catalog, in my home directory, and you can pipe it to Realloc and get something like this. So you have a nice visualization of for each memory allocation. This is actually work in progress because when I was developing the script, some problems arose, and I'm still discussing it with the Realloc creators, but the alpha version is available on my GitHub if you want to check that out. Also, yeah, the interesting part is are the memory allocation functions on OS X are thread safe or not? Well, they are thread safe, but I needed to do some testing to actually know that. And last idea that I want to implement is heat tracing. So it's kind of like code coverage, but the end goal is different. So in code coverage, you're tracing the instructions that will hit inside of the application with the specific input. However, you do that because you want to have a small pool of files for your fuzzing operation as possible. However, with heat tracing, I want to know which particular functions and later which particular code lines will hit when I run specific input. So basically, you could do that with IDA's, well, if you're doing that for IDA. IDA have something like Mac server, but I had a problems with Mac servers, so I implemented this as a DTrace script, but it's not yet public. It's very similar to the idea from the DV Labs guys. So you can reference their blog, and the idea is quite well covered there. So yeah, I didn't mention that. So I want to have this information to actually colorize the graph, but you don't need to colorize graph. And future work. More kernel work, more USDT work. I want to see something like this for V8. V8 is JavaScript engine for Chrome. So I would like to see similar tool that is for Mozilla Firefox for Chrome, or maybe even for Safari. Python-based DTrace consumer, which would be Python bindings. There is something like Ruby bindings for DTrace, but I don't code in Ruby, so I didn't use that. I'm open to ideas, so you can mail me if you have something in mind. Yeah, and that would be it. References are links, so you can just check them out later. Any questions? Yeah.
How safe are these copy in and copy out functions of the kernel space? Because, I mean, you know, one could potentially write a malicious DTrace script to just basically crash everything.
Yeah, that's why when you're doing the copy out, this isn't safe. So you need to actually define the pragma, which stands for pragma the destructive, to be able to do that. And DTrace can be launched only by root. So as root, you should know that you should know what you're doing. But then again, you need to explicitly state that you want to have a destructive, that you want to perform destructive operation. However, with the copy in, these are 100% safe, because they're just basically, you're stating that you want to have some memory that is in the user space, and I want to see what that memory is. So you need to use copy in, because DTrace references that memory, it copies it into its own internal buffers, and then it will present it to you, for example, for trace mem. So its copy out is destructive, copy-ins are 100% safe.
Hello, so my question is about macOS. Apple has that nice feature that when you call ptrace with ptrace deny attach, it disables both future ptrace calls from other processes, but I think it also disables dtrace. Is there any way other than replacing the kernel extension to make it possible to enable it?
Yeah, I have this on my to-do list, but technically you shouldn't be able to, as you stated, you might be able to do that, but yeah, I didn't test that. And I have that on my to-do list. If you do that for some process, Yeah, because iTunes have that. So if you would want to trace iTunes, you probably wouldn't be able to do that via PID provider because it is turned off. So no, you wouldn't be able to change that via DTrace because you would also not be able to DTrace that application, as far as I recall. But I will double check that, and I have that on my to-do list.
Thanks.
Any other questions? Cool. So that concludes my talk.